Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's the only way you can keep me going, inspired, and refreshed. Now, if you find my videos important to your studies, then also don't forget to subscribe. Analyze the Nance frame shown below by constructing the shear force and bending moment diagrams. Also sketch the elastic curve. EI is constant. So another one-story frame. There's no side sway because of the restraint present at A. So the frame cannot laterally move because of the restraint at A. So that's why this is a non-sway frame. Since for portion AB, moment at A is 0, so we only establish MBA. The slope deflection equation is, for that situation, is 3EI over L, and quantity theta near, which is B in this case, minus delta over L, which is 0 because there's no side sway and there's no relative movement between A and B horizontally, even if the loads are there, negligible uh, movement. Then plus moment, fixed moment at B minus fixed moment at A. Fixed moment at B is positive while that at A is negative. So minus 1 half fixed moment at far end. So moment BA is 3 times EI1 over L8. We assume EI equals 1. Quantity theta near, theta B minus delta over L, so 0. Plus fixed moment at B, W L square over 12, so 38 square over 12 minus 1 half. Fixed moment at A, which is negative of W L square over 12. So combining, MBA is 0.375 or 3/8 theta B plus 240. Call that equation 1. Then we have MBC. The far end is ruler. So we use the same formula, but they only vary in fixed moment. So MBC is equal to 3 times 1 over 6 quantity theta B minus 0 minus 44 times 2 square over 6 square minus 1 half 40 times 4 square 2 over 6 square. Fixed moment B is negative P A 4 B 2 square over 6 square minus fixed moment at C, which is positive, so minus 1 half. Fixed moment at C is positive, so you just interchange the squared term. So 40, this time 4 is squared, times 2 over 6 squared. The general formula is PAB squared over L squared, or PA squared B over L squared. Simplifying, MBC is 0.5 theta B, then minus 320 over 9. Call that equation 2. Then MBD, far end is fixed, so 2EI over L. 2 times 1 over 7.5, quantity 2 theta B plus theta D 0 minus 3 times 0. Then there's no fixed moment, there's no load. So that's the moment at B, or moment BD. So it is 8 over 15 theta B, equation 3. Then moment DB is half of this, or you set up 2 times 1 over 7.5 plus times 2 times theta D, which is 0, plus theta B minus 3 times 0. So that's why you have 4 over 15 theta B, equation 4. Then apply equilibrium at B, MBA plus MBC plus MBD equals 0. So MBA is 3/8 theta B plus 240 plus MBC, which is 0.5 theta B minus 320 over 9 plus MBD, which is 8 over 15 theta B equals 0. So from here, only theta B is the unknown. You can solve theta B. Theta B is equal to negative 145.168 over EI. Having found theta B, we can now compute the moments. So MBA is equal to 3/8 of negative 145.168 plus 240. So MBA is equal to 185.562 kilonewton meter. MBC, 0.5 of negative 145.168 minus 320 over 9. So MBC is equal to negative 108.140 kilonewton meter. Then MBD, 8 over 15 of negative 145.168, and that is negative 77.423 kilonewton meter. Then MDB is 4 over 15 of negative 145.168, so it is equal to negative 38.711 kilonewton meter. So from there, we can solve for the reactions, other reactions. So we have AX, AY, those are the assumed direction. MBA is positive, so from slope deflection equation, it is clockwise as shown in the figure. MBC is negative 108.140, so it is counterclockwise in the figure. But remember, counterclockwise rotation is positive in the universal sign convention. Then MBD is negative, so it is counterclockwise also. The figure, call that R sub C. Reactions at D, MDB is negative, so it is counterclockwise. So for AY, summation moment B equals 0 considering AB. So AY times 8 plus MBA, which is 185.562, equals moment of the load 30 times 8 times 4. So AY is equal to 96.805 kilonewtons. Shear at B just to the left, assuming upward, times summation moment at B, R sub C times 6 plus moment BC, which is 108.14, then equals moment of the load 40 times 4, considering BC. So R sub C is 8.643 kilonewtons. Then shear at B just to the left times 8, considering AB, equals moment VA, which is 185.562, plus moment of the load 30 times 8 times 4. So shear at B just to the left is equal to 140.195, while shear at B just to the right, assuming upward, considering BC, summation moment C equals 0, so shear at B just to the right times 6 is equal to moment BC, which is 108.14, plus moment of the load 40 times 2. So shear at B just to the right is equal to 31.357 kilonewtons. For reaction at D, dy, it's shear at B just to the left plus shear at B just to the right. So transmit. So they are downward now by action-reaction principle. So dy is the sum of 140.195 and 31.357. So dy is equal to 174.552 kilonewtons. For dx, considering this column, summation moment B0, so or considering the entire system, summation moment D equals 0. So AX times 7.5 plus AY, which is 96.805 times 8, then plus 40 times 4, then equals this moment here, which is MDB, 38.711. plus R sub C 8.643 times 6 plus moment of the load 30 times 8 times 4. So AX is equal to 15.484 kilonewtons rightward. So dx is 15.484 kilonewton leftward. Another way of computing dx is you sum up moment about B considering this column. So you apply the moment BD. So dx times 7.5 plus mdb plus mbd, which is counterclockwise also. Then you can find dx equal to 15.484. So that is, you add these moments 77.423 and 38.711, divide it by 7.5, and you'll get 15.484 kilonewtons. So that's the other way of computing dx. So we now put these values on the next slide so that we can construct the shear moment diagrams. So let's have the figure, then the results in the preceding slides. So these are the results complete. So we can now construct the shear diagram. First, AY 96.805, so that's upward. Then put the value. Then minus 30 times 8, so we have linear diagram. So 96.805 minus 30 times 8 is negative 140.195. That's shear at B just to the left. It's correct. Then this distance is 96.805 divided by 30 W, and that's 3.2268. Another way is you apply similar triangles. Therefore, this distance is 8 minus 3.2268. That's 4.7732. The area of this diagram is 1/2 of 3.2268 times 96.805. You get 156.185. This one is negative 341.749. 1/2 of 4.7732 times 140.195. Then shear at B just to the right, so we rise 31.357. Then constant, then minus 40, so negative 8.640 R sub C. That's correct. Then for this diagram, dx is leftward, ax is rightward. So if this is the top fiber on this side here, then that's the area. By the way, you don't need to put that area because it is just a rectangle. So from here we move to the right because this is the top fiber by 15.484. Then constant. Then it closes because dx is leftward, 15.484. So that's the shear force diagram in kilonewton. Then for the bending moment diagram, so first moment A0, so it begins here. Then we have positive decreasing 156.185, the value. Then minus 341.749, negative decreasing. So it is negative 185.564. Moment BA, it should be close. 185.562, so they're close. Then moment BC is negative 108.14. Then we have straight line plus 125.428 up to here. So that's 17.288. Then minus this area, 2 times 8.643. So that closes negative constant slope. MBD, and MBD is negative 77.423. So if this is the top fiber, MDB on the other hand is negative 38.711. So we move here, negative 77.423 plus this area, which is 116.30, negatives 15.484 times 7.5 or 116.13. Then you'll get here 38.707, which is close to that, so that's fine. So that's the moment diagram for this frame. So you may shade, you may not. Then for the expected elastic curve for this portion, concave up, then concave down at B, down, down, then there is a portion which is positive here. Then for this part, if this is the top fiber, negative moment means like that. And that's the expected elastic curve. So that's the expected elastic curve. And I hope that you were able to follow the explanation and construction of the shear moment diagrams.